Now, it turns out for pipes, we can create standing waves much the same as we did for fixed strings. The thing we have to be careful of is whether we're talking about a displacement node or a pressure node. They're going to be related, as I mentioned a few slides ago, and long story short is that a pressure node is always going to be a displacement antinode, and vice versa, a pressure antinode is always going to be a displacement node. We can kind of conceptually see that by taking a look at this little cartoon down here, where we have a pipe, you put a little bit of very fine particulate matter in there, maybe some sand, you lay in some gas, it could be air, and set up a speaker that's going to drive this tube, and there's going to essentially be mounds or clumps of the sand. There are going to be displacement nodes. These are going to correspond to pressure antinodes. We can kind of see that looking at this conceptual example over here, where again, displacement nodes are going to correspond to pressure antinodes. If we look at, say, this displacement node right here, and we look at this particle is not moving to left or right at any given time. Therefore, it's going to be a displacement node. Looking at the density of particles, say at this point right here, all the particles are being pushed towards this displacement node, and there's going to be a region of high pressure right here. So it's going to be a pressure antinode. Down here a little bit later, all the particles are being pulled away from this pressure node, and so this is going to be a region of low pressure, or a pressure antinode. A similar story works for the displacement nodes. They're going to correspond to, or the displacement antinodes, they're going to correspond to pressure nodes. The example 1610 kind of shows a loudspeaker that's directed at a wall, and we know at the wall that there can be essentially no displacement, so that's going to essentially be a displacement node. There's going to be no movement there. This is going to be a pressure antinode. We know that the wavelength is going to, or the wave is going to look kind of like this, and we can map out where the displacement nodes will be. The first one is going to be at half of the wavelength, lambda over 2, and then the next one is going to be at 1 lambda, kind of like that. Therefore, the antinodes are going to be at lambda over 4, the wavelength over 4, and 3/4 over 4 for the next displacement antinode. This is going to correspond to pressure antinodes, nodes, antinodes, nodes, and so on and so forth. So really, what we have to be careful of is whether we're talking about displacement or whether we're talking about pressure as we start to look at standing waves in pipes. So let's talk about how we can get standing waves in pipes. Talk about organ pipes, but we can talk about any types of pipes in general. We know that the size, more appropriately the length, is going to be related to the frequency that it produces, and I'll talk about that in the next couple of slides here. But I just want to talk about where the nodes and antinodes are, and I personally always think about this in terms of displacement rather than pressure. I know that if there is going to be an open end, that is always going to be a displacement antinode, and what I mean by that is air is free to move in and out. So here we have air from the blower going into the organ pipe. These air molecules, they're free to move in that direction, they're free to move in that direction. Therefore, it's going to be a displacement antinode, or it would also therefore then be a pressure node. And then there's going to be an antinode, a node, an antinode, and so on and so forth, where particles are free to move and then where they're not so free to move. These are going to correspond to pressure antinodes, nodes, antinodes, and so on and so forth. So let's talk about how the length of the pipe is related to the frequency. We'll be talking just about an open pipe, so it's going to be open at both ends. What that means is there's going to be displacement antinodes at both of these two ends. The particles are free to move at their will in and out of the pipe, more or less as they please. Therefore, it must be pressure, or it must be displacement antinodes or pressure nodes. Now, the easiest possible wave that I could fit in there would have a displacement maximum here, go through the node, zero displacement, and then have the displacement minima right there. If I kind of continued this wave on, going back through the node, reaching the maxima, now I have what looks like one full wavelength going from maxima to maxima. So the length of this pipe is going to be half of the wavelength that you can form in there. We know that the speed can relate the wavelength to the frequency, and so I can write the fundamental frequency is therefore going to be the speed divided by twice the length. This speed is going to be the speed of sound in whatever medium that we're talking about. Very typically it's going to be air, so 343 meters per second. We call this the fundamental frequency, the easiest possible frequency that I can set up in a pipe. Much like for a string, we can set up other harmonics. The only thing we really have to meet is we're going to have two antinodes at each end. The next possible wave I can set up in there is going to have an antinode in the center, and then two nodes in between. It's going to kind of look like that. And we would call this the second harmonic, so we would say n is going to be equal to 2, and in general we can express the wavelength and or the frequency in terms of the length of the pipe and which harmonic we're talking about. Fundamental, second, third, and so on and so forth. Third harmonic, same thing. All we really have to meet is having displacement antinodes there, so there's going to be 4 antinodes and 3 displacement nodes. Now let's contrast that open pipe with a closed pipe. So it's going to be open at one end and closed at the other end. This is kind of like when you blow into your beer bottle and you can you can set up a standing wave in there. Again, open waves are going to have a displacement open ends are going to have displacement antinodes. Air is free to move in or out at their will. Up against this wall right there, the air cannot move. Therefore, we must have a displacement node. So air is being pushed by its neighbors, but it just simply has nowhere to go. The easiest possible wave that I can fit in there is going to go from, say, a maximum at the antinode down to the 0 point, down to the antinode. If I kind of continue to draw this wave out, where I'm going to go now to the minima, and I'm going to go back up through the node to back to the maxima right there, that's going to be one full wavelength right there. This little tiny piece of this wavelength is simply this little tiny piece of the tube here. The length is going to be 1/4 of the full wavelength. We can relate that to frequency much like we did on the last slide, and we can say that the frequency is going to be related to the speed of sound divided by 4 times the length of the tube. The interesting thing about a closed pipe versus an open pipe is being forced to have an antinode here and a node here. When we start to look at the next harmonic that we can possibly fit into the tube, it's going to have an antinode there. By necessity, it must have a node there, kind of by the boundary conditions. The only way we could do that is to go from the antinode through the node, through the next antinode, and now back to the next node. This is actually going to be 3 times the fundamental frequency. What that really says is we're missing the even numbers. We're missing the even harmonics. We jump immediately from the first harmonic to the third harmonic. In terms of writing this with the ends, we can write our frequencies as 4 times the length divided by which harmonic we're on. Frequency is the same, and you notice that these ends don't go 1, 2, 3, 4, 5 like it did for the open pipe, but really we're missing the even harmonics. That is more or less due to the boundary conditions of having a node at one end and an antinode at the other end. Fifth harmonic, more or less the same deal. We'll talk very briefly about resonance here. Suppose we have an open pipe and we try to drive this open pipe with a speaker, much like you might try to drive a string instrument with a like a violin. It's going to respond best at certain frequencies. So if you try to drive this pipe, it's open, it's going to have antinodes at both ends. We can set up different standing waves inside of this guy. We can set up a standing wave that looks like that. We can set up the standing wave that looks like that, or we can have more squiggles in there. The frequency is going to be driven by the length of this guy. So it's going to respond, it's going to be able to set up waves based solely upon this length very well, and it's not going to sustain other waves very well at different frequencies at different wavelengths. So if we look at a plot of the frequency versus the amplitude, which is really how well does it respond to that frequency, we can see that there's going to be different harmonics, 1, 2, 3, 4, 5, and so on and so forth, where this open pipe is going to respond best. It's going to resonate best at certain frequencies. Very much the same with the stringed instruments we talked about last time. There can be interference, and there can be constructive interference or destructive interference. Unlike the string, where we had two waves that were trying to pull the string in different directions, here we have pressure waves, and so these waves are essentially fighting to pull the air in different directions. So suppose we had two sets of speakers that are sending out sound waves. In these charts right here, the regions of dark blue are going to be regions of high pressure, regions of low pressure there. And if we look at these waves right here, the regions of high pressure from each of these two speakers are going to correspond to each other. And so this microphone right here is going to detect a very loud sound. It's going to detect high pressure from this speaker and high pressure from this speaker. So this would be an example of constructive interference. If we look at this setup down here, one key thing to think about when we're talking about interference is going to be the path length, or the length that the sound has to travel. For this setup down here, the path lengths are going to differ by 1/4 of a wavelength. What that really means is when we have a region of high pressure from speaker on top, there's going to be a region of low pressure from the speaker on the bottom, and these are going to essentially cancel each other out, and this microphone right there is going to detect very little or even no sound if you set it up correctly. Let's take a quick look following example 1613 here at constructive and destructive interference. Here we have an amplifier that's driving both speakers A and B at the same frequency, at the same wavelength if you will. We're observing the pressure waves at point P. The difference between A and B is going to be the path lengths that these sound waves are going to travel. This distance A, this is going to be a square, a right triangle here, so this distance A we can write using the Pythagorean theorem as 2 squared plus 4 squared, or the square root of 20. The path length that's traveled by the waves coming from speaker B is going to be the square root of 1 squared plus 4 squared, or the square root of 17. When this difference in path length is equal to a single wavelength, we're going to have perfectly constructive interference. So square root 20 minus the square root of 17, or 0.35 meters if you will. When this is equal to the wavelength, twice the wavelength, 3 times the wavelength, so integer multiples of the wavelength, then we're going to have constructive interference. When it is half of the wavelength, so wavelength divided by 2, 3 wavelengths divided by 2, 5 wavelengths wavelengths divided by 2. Then the regions of high pressure are going to be canceled out by regions of low pressure, and so we're going to have destructive interference. We can, of course, relate wavelength multiplied by frequency to be the velocity, and so the frequency can be written as the velocity divided by the wavelength, and we can put in delta D for the wavelength for both constructive and destructive interference, and kind of come up with what the frequencies should be. So that was constructive and destructive interference for the same frequency, difference being path length. We can also have constructive and destructive interference if we have two waves that have a different frequency associated with them. So we'll be talking about beat frequency here. Here we have two waves that are at slightly different frequencies. We have the red one, we have the blue one and then the red one. Since they're at different frequencies, sometimes they're going to be completely in phase with each other, and sometimes they're going to be completely out of phase with each other. When they're completely in phase with each other, there's going to be perfect constructive interference. So for example, here and here, you can see the waves are essentially adding up. There's going to be perfect destructive interference when the waves are completely out of phase with each other, kind of right there. So we can essentially hear a beat. We're going to hear a whom, whum type of thing if we're listening to this. Musicians use this. They use this to tune their instruments, to say a harmonica or something like that. Of course, that's assuming you can hear that and you're not like mostly tone deaf like I am. Nice thing about it is very simple frequency. It's simply the difference between the frequency A and frequency B, fairly important equation to have. If you're listening to this, however, it doesn't tell you necessarily which one is higher than the other. You can just hear a beat between the two of them. The last key concept that we need to talk about is the Doppler effect, which is going to be a shift in frequency due to a moving observer, a moving source, or possibly both. Let's consider first what happens if we just have somebody that is not moving and say they're whistling. They're sending out pressure waves that are equally spaced apart, and they might be heard by someone over here and someone over here. And we would say, well, observer number 1 is going to observe the same frequency as observer number 2. So frequency 1 would be equal to frequency 2. Now, however, suppose I have this source and it's moving in that direction. Essentially, it's putting out these pressure waves, but it's also walking towards these pressure waves, and they're going to end up being closer together because he's essentially playing catch up to his own pressure waves. So the pressure waves are going to be more densely packed in right here. Now this observer number 2 is going to observe a much higher frequency than observer number 1 would observe. Essentially, this guy would be now running away from the waves that he put out over here, and so they would actually be a little bit further away. You can kind of see this schematically for this fellow that's whistling as he walks away from the police officer. One thing to keep in mind as we look at these is the definition of positive. The definition of positive is going to be going from the listener to the source. Now, in general, what we can do is we can write the frequency observed by the listener to be equal to the speed of sound plus the speed of the listener divided by the speed of sound plus the speed of the source multiplied by the frequency that the source puts out, where the velocity of the listener and so on and so forth is kind of listed right here. Now, we can see that if the source is moving away from the listener, then we're going to have a much lower frequency, and vice versa. If we put our listener over here, then the frequency that they observe is going to be larger, keeping in mind again that positive is going to be defined from the listener to the source. So let's take a look at solving some problems using Doppler shifts. Suppose we have a police car and it's going to have a siren that is operating at 300 Hertz. First, what is the wavelength going to be if the car is not moving? Well, the wavelength is simply going to be the speed divided by the frequency. Speed is going to be sound, so 340 meters per second, and the frequency is 300 hertz, so the wavelength is just going to be 1.13 meters. Now, if we think about a police car that is traveling forward, suppose it emits a pulse, and then it travels 30 meters per second, and emits another pulse, and another pulse. They're going to be more tightly packed in there in front of the car than if we look at behind the car. I mean, the car is going to emit a pulse, and it's going to essentially run away from the pulse it emitted. Then it's going to emit another pulse, and another pulse, and so the wavelength behindhand is going to be a little bit longer than the 1.13 meters. The wavelength in front of it should be a little bit shorter than 1.13 meters. We can write the wavelength in front of it not to be the velocity divided by the frequency, but now the velocity minus the velocity of the police car. Essentially what we're doing is listener to the source is going to be what we call positive, so we're going to subtract that velocity off, and the wavelength beforehand is going to be, or the wavelength in front of the car is going to be 340 minus 30 divided by the frequency of the source, so 300 hertz, and the wavelength in front of the car should be 1.03 meters. Similarly, behind the car, the wavelength is not just going to be the velocity divided by the frequency of the source, but the velocity plus the velocity of the source. So it's going to be equal to 340 plus 30, that whole quantity divided by 300, and we get the frequency behind the police car to be 1.23 meters. Example 1615 just gives you a little bit of practice figuring out what the frequency of a listener should be. Again, it's going to be the speed of sound plus the velocity of the listener, speed of sound plus the velocity of the source, and always defining positive to be from the listener to the source. Here we have the listener being at rest, so that is going to be 0. Can't forget my frequency of the source here. And now it's simply a matter of plugging in 343 and the speed of the source. Example 1616 is much the same. We'll be looking at the same equation. We'll be setting the velocity of the source equal to 0, and now we have a moving listener. Velocity is going to be negative because, again, positive is going to be from the listener towards the source. So I highly recommend you take a look at that problem. And of course, 1617 is going to have a listener that is moving as well as a source that is moving. Both of these velocities will be positive. It's going to be because they're both moving in the direction of the listener to the source. Example 1618 is actually kind of interesting because we're talking about reflection, so there's going to be a double Doppler shift. First, we have a siren that's at 300 hertz. And a wall is going to act as a listener, and then it's going to act as a source, and it's going to be reflecting the wave, and the police car will be the listener. So what we do is we can say the frequency detected by the wall is going to be equal to the velocity plus the velocity of the source, velocity of the wall, or the velocity of the listener, velocity plus velocity of the source multiplied by the frequency of the source. We know that the wall is not moving, so that's going to be equal to 0. The velocity of the source is going to be negative 30 meters per second because we're defining positive to be the listener from the source. Always is the key for this guy. So we go ahead and we plug all those guys in, 340, and then the negative 30, frequency of the source is 300 hertz, and so the wall is going to essentially hear 329 hertz. Then the wall is going to act like the source would not be moving, and the police car is going to act as the listener. So the frequency of the listener, the cop car, is now going to be the velocity plus the velocity of the listener, of the cop car, divided by the velocity plus velocity of the source, multiplied now by the frequency that the wall is reflecting, so 329 hertz, the source now is not moving. Now this direction, or now this velocity of the listener is going to be positive, because positive is now going to be from the listener towards the source, and we can get a double Doppler shift such that the frequency heard by the police car from its own reflection is going to be 358 Hertz. If you were riding in the cop car, then you would essentially also hear the beat frequency. The beat frequency is going to be the difference between those two. So 358 minus 300, you would hear a whom whum 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 occurring at 58 Hertz. The very last thing I want to talk about that's kind of related to the Doppler shift is going to be a shock wave. If you've ever seen a plane breaking the speed of sound, it's actually pretty cool. There's lots of YouTube videos on that. Essentially, if you have an airplane and it's moving very, very, very fast, then you start to get wave fronts piling up in front of the plane. So this is going to be a pressure wave. And there's going to be really a lot of pressure built up in front of the airplane. That pressure is going to result in a boom for a listener, say, on the ground. Now, suppose we have something that's going faster than the speed of sound. So it's putting off these pressure waves, but it's essentially outrunning them. So you can kind of see how, this is a pressure wave when this guy was sitting right here. This is going to be a pressure wave from the plane at that point. And then here we have the one from where it was just about right there, and so on and so forth. So you get this pulse pile up of pressure that's going to result in a sonic boom or a shock wave for a listener sitting at the ground. There is an angle that's related to it. It's also related to the Mach number, the velocity relative to the speed of sound. So how much faster than the speed of sound are you going? And really, I'm not going to make you use this formula so much as be aware of it. It's also kind of interesting. These are very similar to the waves that you see on the back of a boat if you go fishing. And pretty much every surface on the airplane is going to have a shock wave associated with it. You can kind of see that here. There's going to be a shock wave from the front of the plane, from each of the wings of the plane, and from the tail of the plane. Essentially, each surface is pushing air, creating a pressure wave off of it.